so now we're beginning chapter 16-2, and this is where we're going to take the idea of an antiderivative or an integral to the next level. Okay? Here I want you to observe this function. Okay? Just a curve that's just kind of going between two values. The values are between 0.8 and 3.7. Now, the task before us is to find the area underneath this curve. Okay? I want to find the area underneath this curve. How do I do that? Well, like if I don't know any calculus and I don't know anything about it, by the way, the function here is x minus 3 cubed plus 2 times x minus 3 squared plus 1. Okay? So how do I find the area under here? Well, I don't know, but if I'm allowed to just kind of give my best answer, I would probably want to like fill this up with some familiar shapes. One of the easiest shapes you can pick might be some rectangles. So let's actually add a couple of rectangles in here. Okay? So I just draw some rectangles, and, you know, as a general rule, one way to do it is to say, hey, let the left top point of the rectangle touch the curve. So you can see some of these rectangles are actually above the thing, and some of them are a little under it. Okay? If I add up all the areas of these rectangles, I would get an approximation of the area under the curve. Okay? Obviously, this is not a very good approximation. It's pretty decent. But the nice thing about rectangles is the area of a rectangle is very easy. All I have to do is say its length times height. In this case, my width here is uniform. So every single one of these rectangles has the exact same width, but the height is always going to be something like f of x. So like if this is a particular x value, the height is going to be f of x. So it's going to be some change in x, some constant value times f of x. And I want to add it up for all of these rectangles. How you doing, man? You and those fist bumps. Now, obviously, I mean, I could probably do a little better than this, right? What if I just said, hey, let's make all these rectangles a little smaller? So let's kind of maybe make them a little smaller. All right. So now I got 17 rectangles, and it looks a little better, right? I mean, it kind of looks like if I added up all the areas of these rectangles, it's starting to look a lot more like the area underneath this curve. So, in other words, what happened here? Well, the width here actually got a little smaller, okay, for each one of these rectangles, and I added more rectangles. What happens if I add more? You know? Well, now the width is even smaller, and now the area under the curve is really starting to look like it. Okay, so now we're tempted, all right, well, what happens if I just keep adding a bunch of rectangles here, okay? So what happens if I just keep on adding more rectangles? Well, as you can see, the total area of all of these rectangles slowly but surely starts approaching the exact area underneath this curve. All right? Now, this is going back to the previous unit, but essentially what we're doing is we're trying to find a limit here. What is the area under the curve when we let the width of each rectangle approach 0? All right? Meaning each width is going to be some infinitesimally small width here. Notice that this almost looks perfectly like the area under the curve. Now it's going to go backwards because this is Desmos. Okay? So that's the basic idea behind this. The exact area under the curve would be what is the limit of all the areas of these rectangles added up when we let the width of each rectangle approach 0. Or, in other words, if we let the number of rectangles approach infinity. So if we let this be an infinite number of rectangles, we would actually get the exact value under this curve. And that's the basic idea behind an integral. All right? This is actually the definition of an integral, which is what we were working on this entire time. The antiderivative is the integral. All right, go on in. All right, so here in the text we have a couple of examples here. The total area of the rectangle so constructed is, all right, so this means a sum. Let's zoom in on that. This means we're summing up all the rectangles, and this is the height, f of x, and this is the width, some delta x, some constant width. And we're going to let delta x approach 0, or in other words, we're going to let the number of rectangles approach infinity. So here it is. This is the grand definition. The area under the curve, the int is going to be the integral, where we let the limit of as n approaches infinity, where it's the number of rectangles, we add them all up, that's going to equal the exact interval between a and b. So in this section, now we're going to be talking about definite integrals between two exact values, and there's going to be a geometric interpretation to it. It's the area under the curve of f of x between a and b. All right? Now there's a couple of nice things that we could do with this. We can skip this part. This is not that important. This is just a couple of basic examples. So now that we have this basic idea, we can actually do some basic properties of the definite integral, the area under the curve between two particular values. There's actually a way to do this on your calculator too, but a lot of what makes 16-2 really hard is you're actually going to be doing this without a calculator. In other words, we're going to be trying to find the exact value under the curve. This one, you're not going to be using a calculator too much, okay? So there's a couple of basic properties. The integral from a to b is also the negative of the integral from b to a. In other words, you can flip this upside down across the, basically you can rotate it with respect to the origin 180 degrees, but you have to stick a negative on it, and that would give you the exact same area under the curve. All right. Oh yeah, one other thing. If you have a bit of the area under the curve dipping below the x-axis, the area is actually negative, okay? So it's possible in this case to get a negative area. That's something that should be pointed out. I probably should have said that a little earlier. So if you have rectangles that are above the x-axis, we call that positive areas. And if you have rectangles below the x-axis, these are actually negative areas, if you will. So that means if you get a question that says find the total area under the curve, or the total area between the curve and the x-axis, you're going to have to take the absolute value to make sure you're only dealing with positive values. And there's a way to do that. I imagine I'm going to be going over this in class, and I wonder how many of you are actually watching this. Anyway, how about the integral from a to a? Well, in this case, the width of the rectangle is going to be exactly 0, because the distance from a to itself is 0. So the total area is going to be 0. There's a couple of the really basic properties here. The integral of just a constant, remember that from the last unit, you stick an x on it and then you add c. Well, when we do definite integrals, we actually don't have to add c. In this case, we don't actually add a constant. Go on in. Okay? We don't actually add c. In this case, we just stick an x on it, and and that's that. Now, definite integrals, I don't know why it's not actually going over it this way. What you do is you evaluate the integral at b, and then you subtract the evaluated integral at a. In fact, none of this is going to make any sense until we get to the next section. All right. But anyway, that's the basic idea of an integral. There's a few basic properties here, and we're going to go over this in way more detail when we actually hit an example. Also, the average value of a function, that's a misspelling. It's not that. It's function. The average value is just this formula right here. So you're going to evaluate the integral just like you normally would, a to b, but at the front you're going to say 1 over b minus a. That would be the average value over the course of this particular integral. So in this case, the average value would be something like this. Okay? Like this would be the average height, so it's going to be somewhere in the middle right about here. When you do it this way, it'll actually tell you the average height over the interval from a to b, which is pretty nice. Now, none of this is making any sense to anybody until we actually get to a problem. So here's our first serious thing that we're going to be dealing with here. The first fundamental theorem of integral calculus, integral being calculus 2. And that is this. The derivative of the integral is the original function. Okay? Meaning, you know how we were saying the integral is the antiderivative? Well, the derivative, you could think of it as the anti-integral, if you will. Basically, they should cancel each other out. But with integrals, you have to be a little bit more specific, okay? If you are taking the integral from a constant up to a value x, okay, and you take the derivative with respect to x, then you're going to get f of x. So the key here is you have to make sure that this top value is x when you take the derivative of it, and that will equal f of x. If not, you have to rely on this rule right here to switch places. Put a negative out front, and then take the derivative. So let's see a couple of examples of that. This is actually super easy. So what's the derivative of this beast? Well, because I'm taking the derivative with respect to x, and x is actually the upper value, the answer is just going to be 1 over cosine squared of x. Pretty easy. What's going on?
What's going on? How are you?
All right, so I just relocated. Somebody relieved me from the bathroom duty. So here we go. The derivative of this integral, well, again, we check to say, is this x the same as this x? It is. So the derivative of this integral is just going to be 1 over 1 plus x squared. And that's it. It actually doesn't really matter what this constant is. All right, so if we look, yeah, 1 over 1 plus x squared. This last one, it's the derivative, but now x is actually in the lower bound. So we're going to apply that first integral rule, which says I can actually stick a negative out front and have these guys switch places, and then I can apply the derivative with no problem. So I am going to have these guys switch places, stick a negative out front. I probably want to bring the negative out front here. This is a typo. The x should actually be up here. They did apply the negative. The x is supposed to be up here on the upper bound. Then you take the derivative, and it'll be negative 1 over 1 plus x to the 4th power. Okay? Now, that's not the most impressive thing. The main thing you're going to be dealing with today is this one, the second fundamental theorem of integral calculus. Okay? So here we say, all right, if you are going to take the integral from a to b, it's this one right here. Actually, let's see, do they actually do it right here? Here you go. The integral from a to b is just going to be the integral evaluated at the upper bound minus the integral evaluated at the lower bound. Okay? So the integral of the upper bound minus the integral of the lower bound. And this time we're not adding any c's or anything crazy like that. Okay? That's the basic idea. So if you're pretty comfortable with doing integrals, now we're just going to add one more step. That's going to be evaluating the integral at the upper bound minus evaluating the integral at the lower bound. Let's do an example. Okay? So, some of these integrals we should be able to do in our heads. So what's the integral of x to the 5th power? Well, it's x to the 6th power over 6 plus c. But so when we're doing definite integrals, where we have like a lower bound and upper bound stated, we actually don't need to state the constant. We don't need to have a plus c, okay? In this case, my upper bound is 3 and my lower bound is negative 1. So all I need to do is evaluate at the upper bound and subtract evaluating this at the lower bound. So what's this going to look like? Well, excuse me. I'm going to pull out my handy dandy calculator, and I'm going to say, okay, 3 raised to the 6th power over 6. So this is me evaluating the integral, which is x to the 6th power over 6, but I'm evaluating it at 3. Now I'm going to say minus, okay, alpha f1. I just type in whatever integral that I got, open burrito negative 1, and I'm going to raise this to the 6th power over 6. So again, I just take my integral evaluated at the upper bound, and I subtract the integral evaluated at the lower bound, and my answer should be 364 over 3. Now I know I said I'm not using my calculator here because I need my exact value. However, if you use the function of, if you use the fraction function here, alpha f1, and you press evaluate, most of the time, the TI-84 will actually give you the fraction, saving you a lot of time. I mean, if I were to actually try to do this by hand, it would actually take me a lot of time. So whenever possible, try to use your calculator if possible, but sometimes you're not going to get that far. So how about this one, the integral from 0 to 4 of the square root of x. Now again, we should be pretty comfortable with this at this point, but we want to change this to a calculus friendly format, so we change this to x to the 1/2 power. We add 1 to the exponent, and that's going to make it to the 3/2 power, and in the denominator we'll have 3/2. But we do a little bit of keep change flip, and it'll be 2/3 x to the 3/2 power. In my opinion, whenever I'm trying to do something like this, I might actually put this on my calculator. So let's try it. Alpha f1, try to use this fraction function whenever you can, 2/3, and then it's going to be x to the 3/2 power. And I can already tell you this is not going to give me an exact value very easily. But let's see what we can do. Okay. So now that I have my integral programmed in my calculator, I'm going to hit variables, y variables, enter, enter. And I'm going to evaluate this at 4. And then I'm going to subtract this integral evaluated at 0. So it actually helped me out here. The exact integral here would be 16/3. Let's see if that's right. Yep, 16/3. So I used a little bit of calculator know-how, and I made my life a lot easier. Actually, they did a lot of the work right here. Isn't that nice? All right, how about this one? The integral of cosine is sine. Okay, so we should have that memorized. And then it's going to be the sine of 2 pi minus the sine of pi. Well, if I know my unit circle, I don't even need a calculator for this one. The sine of 2 pi is 0, and the sine of pi is also 0. So it's going to be 0 minus 0, which is a 0. All right, this one, we're going to have to split this one up a little bit. This is going to be 4 over u cubed and u squared over u cubed. That means this one's going to be 4 u to the negative 3 power, and this is going to be u to the negative 1 power. The integral of 4 u to the negative 3 power is going to be negative 12 u to the negative 2 power. And this is just going to be 1 over u, so the integral of that should be the natural log. If we know our integral rules, this should be pretty simple. So the natural log of the absolute value of u. There we go. And we do a little bit of, oh, did I do that wrong? Negative, oh, right, you put the negative 2 on the denominator. Yeah, that's right. I'm trying to do this verbally. 4 divided by negative 2 is negative 2u to the negative 2, and natural log of u. Now, you got to evaluate this at 2 and 1. If I plug in 2 right here, this is going to be 1 over 4. So this first one's going to be negative 1/2. This one's also going to be the natural log of 2. Okay? Then that's going to be the first part. Then I have to subtract this quantity evaluated at 1, where it's going to be negative 2 plus the natural log of 1. The natural log of 1 is 0. Okay? So that's basically it. So negative 2. So I'm going to have to say negative 2 over 4, negative 1/2, negative 2 here. So negative 1 over negative 1/2 plus 2 would actually give you 3 over 2. And the natural log of 2. Now, when you are writing your answers out, you're not going to give me the decimal. You have to give me the exact value. It's going to be 3 over 2 plus natural log of 2. If you don't, you're going to get it wrong, okay? I don't want you to give me the decimal approximation. I will count it wrong, okay? Now, we're going to do some homework examples here in just a second, just so we can actually see a little bit more work here. All right, I'm not going to throw you to the wolves. Using substitution with the definite integral. Again, this is u substitution. Should be pretty comfortable with this by now. But basically, you want to look and see, does my u substitution have the derivative in the integral? So here I look at this. This is tangent to the 5th over cosine squared of x. Well, if I let u equal tangent of x, I know that the derivative is secant squared, or 1 over cosine squared. So that means the derivative is in the integral, 1 over cosine squared dx. So when I do a u substitution, this is going to be u to the 5th power du. Okay? Now they do a weird trick here, which I personally do not do. What I normally do is I get the integral out, and then I just evaluate the integral at pi over 3 and 0 and be on my way. Okay, and the tangent of pi over 3 should be the square root of 3, because tangent is sine over cosine. Sine of pi over 3 is square root of 3 over 2. Cosine of pi over 3 is 1 over 2. So the square root of 3 over 2 over 1 over 2 is the square root of 3. So that's why they get this. And for me, you would basically leave it like that. Okay, you would have the square root of 3. Where is this 6 coming from? Oh, I see. There's a typo here. It would be the square root of 3 to the 6th power. When you type that in your calculator, you'll get 27. So, if you don't believe me, there's a square root of 3. Jeez, square root of 3, right arrow, raised to the 6th power. It'll be 27. So that's a typo. This is supposed to be up here. Square root of 3 to the 6th power is 27 over 6, which simplifies to 9 over 2. Great. They do it another way here, where they actually substitute pi over 3 and 0 into the integral. I've seen some professors do this. You can do it this way too. What they do is they say let u equal tangent of x. Now if we evaluate u at pi over 3, then pi over 3 is just going to become the square root of 3. And if you evaluate it as 0, you're going to get 0. So they actually change the upper and lower bound to something like this. In this case, it works out pretty okay. It's about the same amount of work. It's not what I normally do, but if you feel comfortable doing it with this way, that's fine. So u to the 5th power du, you would then say this is u to the 6 over 6. You'd evaluate it at the square root of 3 and at 0, and you get the same answer, 9 over 2. Either way is totally fine. All right, so here's an example. We're going to be doing this a lot in homework anyway, but here I say, hey, let u equal 4x plus 1. The derivative of that would be 4 dx. In order to have permission to do that, I have to have a 4 dx here, but in order to do that, I have to have a 1 over 4 out front, because 1 over 4 times 4 will allow me to put the 4 in the integral that I need. So when I do that, I'm going to get this. Nice. So it'll be the square root of u, or u to the 1/2 power. When I do the integral, I will have not u to the 1/2 power, but u to the 3/2 power, all over 3 over 2. With a little bit of keep, change, flip, it'll be 2/3 times u to the 3/2 power. I got to evaluate it at 25 and 9. Okay, I stick the u back in. U is going to be 4x plus 1. Put the u back in there, and I evaluate it at 25 and 9. All right, and I guess they want me to do that, so okay. Let's try it. Alpha f1, 1 over 4, and let's do this. The first one is 2 over 3. And let's do it the easy way. Let's go y equals, clear this out. I'm actually going to write this in here, okay? So 1 over 4, okay, alpha f1, whoa, not that one. What is going on with me today? 2 over 3 x to the 3/2 power. There we go. So I actually type my integral in the calculator. Okay. I come back out here and I'm like, okay. Enter. Let's evaluate this at the upper bound, which is 25. And let's subtract the exact same integral. Evaluated at 9. So the answer will be 49/3. So this time it worked out. I did not get a decimal, so I feel pretty happy about that. Yeah, perfectly fine. So as you can see, it's pretty easy. Now here we got something called the trapezoidal rule. This is the last thing that we're going to be covering, and then we're going to do a couple of homework problems here. The trapezoidal rule says, what if I have some data points? So instead of having a continuous function, what if I instead have a bunch of data points and I still have to find the area underneath this weird curve? Well, the trapezoidal rule will be the way to do that. I mean, you can't take an integral of data points, all right? We actually have to come up with some way to make a function that connects our data points, and that will give us our integral, more or less. The trapezoidal rule says, instead of drawing rectangles, let's actually draw trapezoids, and then we'll find the area of every trapezoid. All right? Now, the area of a trapezoid should be 1/2 the first leg plus the second leg multiplied by the width. Okay? Now, doing it this way is, and then we got to sum it all up. When we do it this way, we find that the area, when we add these all up, we look and we say, hey, we can factor out this delta over 2 thing all the way over here, and we're going to get this. And you'll see we'll have the first y value, 2 of the second, 2 of the third, 2 of the fourth, and then we'll have 2, 2, 2, 2, 2, 2, 2, and then 1 at the very end. So we can actually stick a 2 out front here and just say all the middle values here. So 2 times all the middle values plus the final value y. Okay? And this actually gives us an approximation for the area under a curve, where delta x is the width of the trapezoid. Okay? Let's see an example, shall we? No, I want data. Here we go. Let's do this one. Instruments on board a ship traveling on a path heading due north show the following readings for the velocity in kilometers per hour over an interval of 10 hours. Give an estimate of the distance traveled. So again, like I said in class a long time ago and recently, in order to find distance and we're given velocity, we want to take the integral of the velocity function. But we don't actually have a velocity function. All we have are data points. In this case, we would do the trapezoidal rule. So delta x means what's the change in x every time? Well, the change in x every time is just 1. So that's nice. So the first part of the trapezoidal rule says delta x is just going to be 1. So the first part's going to be 1/2. Then the happy stuff. All I got to do is just write down my y values. So I would give 12 plus 2 times quantity, all the middle values. So I'd add up all these middle values and multiply that result by 2. Close quantity, and then plus 17. That would be that. So in order to do that, literally I would just type this on my calculator and I'd walk away. I'd be happy. So 1/2, 12 for the first value, and then 2 times, okay, and then just write down all of these values up to 14, close parentheses, then plus 17. When I type this whole bad boy into my calculator, an estimate for the distance traveled is 160.5 kilometers. Piece of cake. Now this part, continuous money flow, we're not going to cover that until much later. I feel like that's a little bit of a waste of time. If we have any extra time at the end of this unit, we'll go back in and swoop in and just kind of pick up all this stuff. But it's a very famous formula where it's like the principal times 1 plus r over n raised to the n over t power. Honestly, there's an app on the calculator that they want you to learn. It's called the Finance app, and that's where you can get a lot of this stuff and make it easy. The area would be the principal times e raised to the r times t power. It's honestly not that important, but we'll go over it again, especially when we get closer to the IB exam. So stay tuned for that. But for now, let's actually put that one in the bin, and we'll get back to that at a later date. Okay? So let's move on to a couple of nice homework problems. All right, so let's look at a couple of homework problems here. This should be pretty quick and easy. So I've elected to do some of the ones in blue, mostly because I think that's going to help you with a couple of these. It's all pretty easy. You just have to take the integral, evaluate at the upper bound, minus the integral evaluated at the lower bound. So if I look at D, okay, which is going to be the integral from 2 to 2, cosine of t minus tangent of t dt. All right. So this one's a special this one's a special one. In fact, I don't even really need to do anything here because it's totally opposite what you got to do. The lower bound is equal to the upper bound. So this is kind of a trick question. The integral for that is just 0. All right. So again, I don't have to like actually do anything serious here. The integral of cosine is sine, and the integral of tangent is it's like the natural log of the absolute value of cosine or something like that. It really doesn't matter because you're going to evaluate them both at 2. So you evaluate the upper bound at 2, whatever it is, it's going to be f of 2 minus f of 2. It's going to equal 0. And in fact, this is one of the identities in the actual PDF. So this one's actually super easy. So it's kind of a trick question. So that's fine. What about this one? So let's do f, the integral from 0 to pi of cosine of theta d theta. So this one's actually, all of these in the first section here, number 1, are meant to be like one-step processes, supposed to be super easy, nothing too crazy. So with this one, the integral of cosine is sine. So when I do this, the integral of cosine is just sine of theta. And we evaluate it at pi and 0. By the way, this right brace is a shorthand way of saying, all right, evaluate it at the upper bound and evaluate it at the lower bound. Okay, so when I evaluate this at the upper bound, I'm going to get the sine of pi minus the sine of 0. So basically I just plug in pi and I plug in 0 and I have to subtract them. Well, if you know your unit circle, which you should, sine of pi is 0, sine of 0 is 0. So the final answer here is actually pretty easy. It's 0. All right, no big deal. All right, so let's do a couple that are like maybe a little on the harder side. Okay, 2b looks like this one. So it's going to be the sine of pi times the natural log of x all over x, and this is the integral from 1 to the square root of e with respect to x. What does that look like? Okay, so this is my original integral right here, and clearly what I want to do is I want to do some kind of u substitution. Okay, so I look at this and I'm like, all right, what would be the best u substitution? Well, the only way you can do a u substitution is if the derivative is in the integral. In this case, after a little bit of inspection and just using my mind and stuff, I know that if I let u equal the natural log of x, then the derivative will be 1 over x dx. Okay, so that's what I do here. I say let u equal the natural log of x, which means that, oh, this is supposed to be du. Du will equal 1 over x dx, which is what I've got here. I've got 1 over x dx. I have it hidden right in plain sight. So I can substitute the 1 over x dx for du. That's what that becomes. And the natural log of x just becomes u. So that's pretty good. Now, I'm almost done. I look at this and I'm like, oh, geez. I need another substitution here, don't I? I need another substitution here. Well, if I let w equal pi u, I just made another substitution here, then dw will equal pi du. All right, because when I take the derivative of this side with respect to u, it's just going to turn into pi. All right, well, in order to get pi du on the outside here, I have to multiply by 1 over pi, because it'll be 1 over pi times pi du. So I have 1 over pi times pi du. So that's where this 1 over pi comes from. Pi u is going to turn into w, and that's happy times, happy times. So now I can take the integral of sine of w with respect to w. When I do that, the integral of sine is negative cosine. And now I just plug things back in. So w was equal to pi u, so pi u, but u is equal to the natural log of x. So it's going to be negative 1 over pi cosine of the pi of natural log of x. And it's going to be evaluated at the square root of e and 1. Okay? This is the standard way of representing your definite integral. You have the right brace here with the upper bound on the top, the lower bound on the bottom. Okay, so we go ahead and do that. Honestly, this part here is pretty basic. You got to plug these in. All right, so square root of e is just e to the 1/2 power. So first of all, wherever we see an x, we're going to type in e to the 1/2 power. And then you say minus, okay, well, same integral, but wherever we see an x, we're going to type in a 1. Now, there's a simple rule with natural logs and logs in general. The natural log of e to the 1/2 power, you can actually think of the e and the natural log canceling out. So they actually cancel out, and you're left with 1/2. So pi times, and I'm all within cosine here, pi times 1/2 is just pi over 2. So here we have to use a little bit of knowledge about logarithms and natural logarithms in e. The natural log of e is going to cancel out the e. Also, e to the natural log will also cancel out the natural log. That's another thing you do. So anyway, this becomes the cosine of pi over 2 on the left. Over here, the natural log of 1 is always 0. In fact, the log, any log base of 1 is always going to equal 0. So 0 times pi is just 0. All right, that's pretty good. So now I use my unit circle and I say, all right, the cosine of pi over 2 is just 0, and 0 times anything is just 0. So the left side just becomes 0. I still got the minus sign. The cosine of 0 is 1, so I'm going to be left with negative 1 over pi. Negative, negative becomes a positive, so the answer is 1 over pi. And if you're wondering, can't I just do the decimal representation? The answer is no, because all of these are supposed to be in exact values, okay? I'm not going to accept decimal approximations. No, no, no. I want exact values, so you're going to do this the right way. Okay, and that means knowing a little bit about your unit circles sometimes is going to be pretty handy, and knowing a little bit about natural log and e is also going to be pretty handy. If you're thinking this is too much work, well, I'm sorry, but that's what higher level is all about. And when you go to college, they're going to expect you to have a pretty sound foundation in this sort of thing. So, you know, it's a good idea to get used to it now before we head off to college and your professor says you don't know what the cosine of pi over 2 is. Okay? So let's keep going. All right, so the next one is 2f. That's going to be the integral from e to e squared of the natural log of x over x dx. This one seems pretty standard. We should be able to do it. So first of all, I copy my integral down up here, and I want to say what u substitution also has its derivative in the integral. Well, if I let u equal the natural log of x, then the derivative is going to be 1 over x dx, which is in the integral. 1 over x dx is in the integral, so I substitute 1 over x dx for du, and natural log of x just becomes u. Nice. So now I do the integral, so it's going to be u squared over 2, but when I do my substitution, u will actually become the natural log of x. Cool. So that's what I do here. And I have to evaluate it at e squared and e. So first things first, I plug it in. So wherever I see an x, I'm going to type in e squared, and wherever I see an x, I'm going to type in e. Again, the natural log of e squared, you cancel out the e in the natural log, and it just becomes 2. And again, the natural log of e to the 1 power, this cancels out and just becomes 1. All right, 2 squared is 4. 4 over 2 is what this is. And over here, 1 squared is just 1, so this is going to be 1 over 2. 4 over 2 minus 1 over 2 is 3 over 2. There you go. So again, a little bit of algebra know-how actually saves the day. Not bad. Let's keep going. All right, last problem we're going to cover today, because the rest of these are pretty easy. You know, find the average value. There's a formula. Find the derivative. This is easy. All of these should be pretty easy, you know. Let's do this last one, which is kind of on the harder side, I guess. The integral from 0 to pi over 4 of e to the sine 2 theta power times cosine of 2 theta with respect to theta. What's that look like? Well, I copied down the integral right here, and again, I want to do a u substitution. That's usually my bread and butter. The only time you're allowed to do a u substitution is if your derivative is also in the integral. So if I let u equal sine of 2 theta, then the derivative will be 2 cosine of 2 theta, and this should be d theta right over here. Let me fix that. D theta. There we go. So the derivative of that would be 2 cosine of 2 theta, because you do the chain rule, the derivative of the outside times the derivative of the inside, d theta. Almost there. We have cosine of 2 theta d theta, but we don't have the 2. So we multiply by 1, which would be 1/2 times 2. That puts the 2 next to here, and we're happy. So that's where the 1/2 comes from out here. U is just going to be sine of 2 theta. So this actually becomes the integral from 0 to pi over 4 of e to the u with respect to u. Now we're happy. So we do our integral. The integral of e to the u power is just e to the u. And then we plug back in u, which is sine of 2 theta. And this is going to be evaluated at pi over 4 and 0. So I plug that in. So pi over 4 is going to go here, and 0 is going to go here. I subtract the upper bound minus the lower bound. A little bit of distribution, so 2 over 4 becomes, 1/2. So pi over 2, and 0 times anything is just 0. The sine of pi over 2 is 1, and the sine of 0 is 0. So if you know your unit circle, this is going to be a piece of cake. Cool. Well, e to the 1 power is just e. E to the 0 power is just 1. Anything to the 0 power is just 1. And then the final answer, when you just simplify it a bit, is going to be e minus 1 all over 2. Piece of cake. All right. Now, the rest of these homework problems, I mean, we can work on them together as a class. It's pretty easy. This one, you have to just sort of evaluate it at 3x and x and stuff, and you're going to see that it actually is going to equal a constant value. So number 9, I want you to actually find the value. Find the constant value that this is going to be at. Let's see. Oh yeah, and number 14, you got to use the trapezoidal rule. All right, got to use the trapezoid rule. And that's that. If you have any questions, please let me know. Again, this is kind of a doozy, so I'm going to try to help you out as best as I can. In class, we want the exact value. I already did the answer key for all of these, so I think almost all of them should be very doable. There's a couple in here that still are like really a big deal, and you might get like a weird answer that requires a lot of algebra. We'll work on that together as a class. You'll see when you see it. But yeah, I'm here to support you. Let me know. Take care, and I'll see you in the next video. Bye-bye.